Hello and welcome to our symposium on the state of the Salish Sea. As you're signing in, please feel free to use the chat box and share with us where you're watching from. And instead of using your town or city, please choose the river or inlet that is closest to you. Well, it's great to see all these coming in. Thank you. Thank you for joining us and spending your Wednesday afternoon with us. I'm Ginny Broadhurst. I'm director of the Salish Sea Institute. The Salish Sea is a special place. It's home to many of us. We have nearly indescribable connections with the Salish Sea. Though I've lived 35 years in this region, my history, and I would guess many of yours, is short here in comparison to the tribes and First Nations that have lived here since time immemorial. I'm talking to you from Bellingham, Washington, which is the ancestral homelands of the Lummi Nation and the Nooksack tribe. I'm fortunate to not just live on this land, but privileged to learn from generous co-Salish teachers and knowledge holders. The Salish Sea Institute at Western Washington University works to protect and restore the Salish Sea. One of the ways we do that is by teaching the next generation and advancing a deeper understanding of engagement with place for students. In 2019, we worked with faculty to create a first ever Salish Sea Studies minor that was formally approved by Western Washington University. We've already had a few students graduate with a minor, and we expect a few more to graduate this June. In this photo, you can see on the left, students were actually helping to provide input to the creation of the minor. And on the right, our very first two students to declare a minor in Salish Sea Studies, Faith and Zara. The Salish Sea Institute is also the administrative home for the Salish Sea Ecosystem Conference. This is a significant forum for scientists, managers, and others to share research and projects focused on the Salish Sea. And it's equally as important as a place where we get to know each other, to build relationships across the border. There will be a conference in 2022. It'll be virtual, and more details will be coming up on that soon. Check our website for information there. I see part of my job is helping people to erase jurisdictional boundaries so they can see the Salish Sea as one water body. This picture is taken from South Pender Island in the Gulf Islands in British Columbia, and it looks out across the international border towards Stewart Island and other areas, the Strait of Juan de Fuca. Another part of my job is to make science available about the Salish Sea. And today we're going to take on both of these tasks. In 2017, I was hired as the first director of the Salish Sea Institute. I knew that there had been no comprehensive report done about the Salish Sea since 1994. So I want to give you a little bit of context for that time frame. In 1992, there was an environmental cooperation agreement between British Columbia and Washington State, signed by Governor Booth Gardner and Premier Mike Harcourt. The agreement created a BC Washington Marine Science Panel that created the 1994 Shared Waters Report. This report can still be found online if you do a search for it. And it's also listed in the references of the Salish Sea, State of the Salish Sea Report. The panel at that time found that water quality on both sides of the border was a high priority issue requiring immediate and joint attention. Much collaborative work occurred as a result of the agreement and the report. Another important time to mention now is the naming of the Salish Sea. Starting in 2007, the Salish Sea name that allows us to refer to this water body as one system was adopted by the Coast Salish Gathering. Subsequently, in 2009 and 2010, Washington State and British Columbia also formally adopted that name. This beautiful map was created by Stephen Freeland at Western Washington University in consultation with Bert Weber, who also was involved in championing the adoption of the name. It's been used in many, many places to open people's eyes to the connections of these waterways. And it's literally been my calling card as I've worked to raise attention to the Salish Sea. There's been a lot of work happening to protect and recover our waters. There are many excellent reports out there that have been done to assess various water bodies that are part of the Salish Sea, including Puget Sound, the Georgia Strait, individual watersheds, and there are reports that look at individual species. But since 1994, there has not been a report that addressed the ecosystem as a whole. The Institute crafted a proposal for a State of the Salish Sea report several years ago, and we were awarded a philanthropic gift to do this work. I was extremely lucky to find Kathryn Sobocinski willing to take on the job of lead writer. As we built the report, we had a lot of contributors and reviewers who made the report possible. We're so proud that we were able to employ some student help from Western. The bulk of the graphic layout was done by Nick Pinkham, who was a student who just graduated from Western winter quarter and stayed with us into spring quarter to finish this up. Lily Thomas, another student, worked on the reference organization, which was a huge task. Additional students were involved in writing and photos. Clarity Scientific was fabulous to work with for editing and more. And I want to give a big shout out to Natalie Beloy, who works with me at the Salish Sea Institute and had her hand in many aspects of this report, and who's an amazing colleague. Natalie, Kathryn, and I together wrote the last section of the report, section 7. You can download the report for now. That's the only way to view it. The link was in your registration information and is widely available. It's up here. We're getting requests for printed copies, and in fact, we're raising funds to make that happen. If you're inspired by what we're doing, please consider making a gift to the Salish Sea Institute. And thanks so much to those who have already donated during the registration process. Tomorrow just happens to be Give Day at Western, and we have a special page that's set up for this. So without further ado, I want to get into the main event here. Our speakers today are going to share some important work that's featured in the report. Our focus today is on the science. That's where these speakers are working. That's their space. I know there's a lot of policy questions arising, and I saw them in the registration process, but we're not really going to dig into policy today. We'll hang on to that for future symposiums. I want to let you know that we do have the Q&A button live. We have so many people involved. We definitely won't be able to get to all questions, but we really want to see what's on your mind for questions. So our first speaker for the report is our lead writer, Kathryn Sobocinski. You can read about her in the program and in the front matter of the report, but I want to tell you a few things that you won't find there. She is dogged in her pursuit of science. She has extremely high standards. She cares deeply about this place, the Salish Sea. And she took our vision for the report and she took it to a much higher level. She shoots for excellence, and she helped us get there with this report. And it's just been a real privilege to work with her. And I'm going to stop sharing my screen and turn it over to Kathryn.
Thank you, Ginny, for the nice introduction. It's a real honor to be here today and to have so many people interested in this project. I'm an assistant professor in the Department of Environmental Sciences and the Marine and Coastal Science program here at Western. And while I'm the lead author for this report, the whole project received tremendous support, from brainstorming ideas to putting the finishing edits on design at 3 a.m. from both Ginny Broadhurst and Natalie Beloy at the Salish Sea Institute. So I'm indebted to them for their help and prompting along the way with this project. I'm speaking today from Bellingham, Washington, which is the ancestral lands and waters of the Lummi Nation and Nooksack tribe here in the Salish Sea. It is with gratitude and humility that I call this my home. The Salish Sea is a biologically diverse inland sea that spans the international border and the lands of numerous First Peoples, is surrounded by mountainous watersheds of spectacular beauty, and features a rich cultural history. For over 10,000 years, people have lived along the shores of the Salish Sea and among its surrounding rivers and forests. Today, the region is home to over 8 million people, and that number is rapidly growing. When we look out onto the beauty of the Salish Sea, we miss what's beneath the surface, both literally and figuratively. We know the ecosystem has seen profound change, but we have only recently started to think about this inland sea as a whole entity. While much excellent work has been done in Puget Sound and the Strait of Georgia, less research has spanned the bioregion, considering the Salish Sea as a whole social ecological system. And it is a diverse system, which makes generalizations, both in impacts and in ecosystem function, a challenge. So when we ask, what is the state of the Salish Sea, there really is no simple answer. But this complex ecosystem has a suite of complex problems, all interacting in space and time. This synthesis report describes the pervasive problems, identifies emerging concerns, and invites readers to engage in tackling the cumulative impacts of an increasingly affected system. The objectives for the report were to provide a credible assessment of the structure and function of the Salish Sea estuarine ecosystem, emphasize two overarching threats to ecosystem function, those being population growth and the related urbanization, and climate change, and to describe the key ecosystem impacts of these. Also to identify information gaps and emerging concerns, and to highlight the types of actions that can be taken for conservation and/or changing the course toward restoration and recovery. These objectives were developed during the project scoping through the work of a report advisory committee, whom I'd like to acknowledge here. Without this group of people to guide the early stages of this project, I would have been floundering a lot more than I was. This advisory committee provided guidance and feedback during both the scoping and report construction, with lots of constructive comments along the way. I'd also like to thank a number of informal contributors and section reviewers that contributed to reviews of technical sections and provided conversation about some of the things that I, as the lead writer, was maybe not as well versed in as they were. So thank you to those people. And also to the peer reviewers who provided excellent feedback and constructive critique that improved the final product. We thank you all and appreciate the contributions you made. Even if it was seemingly small to you, it bettered the report. So the report is functionally in 7 sections, and I've put those here to give you some idea of where we're headed. I'm going to walk through these in some fashion throughout this talk. One thing I wanted to mention is that at the end of each section, we have a number of vignettes. We had over 20 contributed vignettes authored by an array of scientists and practitioners throughout the Salish Sea, bringing unique voice and perspective to a variety of topics. Dr. Emily Howe from the Nature Conservancy will be speaking about one of these vignettes later in the hour. These authors who contributed these pieces voluntarily represent US, Canadian, and Indigenous voices, and some of them range from highly technical to non-technical summaries, and really added quite a bit of variety and perspective to the project. In addition to the text and vignettes, a number of new map products were generated by Dr. Aquila Flower here at Western Washington University. She will explain the challenges and rewards of working with maps later in this session. The US, Canada, and tribal and First Nations lands share a geomorphic history heavily influenced by past ice ages, numerous freshwater inputs, and an interconnected set of inland waterways connected to the Pacific Ocean, through the Strait of Juan de Fuca, seen here, and Johnstone Strait to the north of the Salish Sea. This unusual perspective, I feel, captures the essence of the Salish Sea and much of its variety and contribution of major features like the Fraser River seen here. The vegetation communities of the uplands reflect highly variable local climate conditions and microclimates, and the connectivity between the upland mountainous regions and the Pacific Ocean runs all throughout the Salish Sea. In short, the Salish Sea relies on strong connectivity from mountains to the Pacific Ocean, and it's a system very much influenced by both, as we'll get into here shortly. Freshwater input is a defining feature in this system. It is what makes this inland sea an estuary. This map highlights a few of the major rivers draining into the Salish Sea, given an average discharge in cubic meters per day to show that the different rivers are bringing in different contributions of freshwater into this system. This is one of Dr. Aquila Flower's maps that was produced for the report. As you can see here, the Fraser River is the dominant freshwater source. And when we plot the average discharge in cubic meters per day against some of a handful of rivers from the Salish Sea, you'll see just exactly how much greater contribution this river system makes in terms of freshwater than the other river systems. It's not only bringing fresh water, but it's also bringing sediment and nutrients like silica that are critical to marine life from the uplands and mountainous regions. This image from the European Space Agency's Copernicus satellite shows exactly how profound that plume of sediment and fresh water is coming out of the Fraser River. This is a very important feature within the Salish Sea. This freshwater input drives what is called estuarine exchange flow, which then drives circulation throughout the Salish Sea. So in this figure created for the report and adapted from a figure by Dr. Parker McCready at the University of Washington, we've got here sort of a visualized estuary looking from north to south, say, and let's envision this river as the Fraser River coming in with fresh river water on the surface because it's less dense than the salty ocean water, which is coming up from through the straits and up from the coast. These two water masses mix with tides and currents due to some turbulent mixing. And then we get this countercurrent that's created, generating exchange flow, whereby the fresh water moves out and the salty ocean water moves into the Salish Sea. This turbulent mixing caused by the tides reduces stratification, which is the separation of water masses of different densities. But the remaining density differences between the freshwater and saltwater create this exchange with the deeper ocean water coming in at the bottom as the surface water exits. This is an important concept for understanding some of the circulation around the Salish Sea. So this estuarine exchange flow drives this circulation. And in this plot on the left, we see this deep water, salty ocean water coming in to the Salish Sea and circulating around. And then that actually, the water going out is also fairly saline. The contribution of fresh water is much less than overall ocean water coming into the system, but it's circulating around and then exits either through the Strait of Juan de Fuca where it entered or through Johnstone Strait. This circulation promotes high productivity. So these nutrient-rich ocean waters, as this salty ocean water is coming in, it tends to contain lots of nutrients. And because it's circulating throughout the Puget Sound and Georgia basins, it's bringing this nutrient-rich fluid throughout. So the movement of water transports nutrients, sediments, and organic material throughout the Salish Sea. The rate of this movement varies. And the drawing that I have here is from a paper that talks about the residence time, just how long that water stays within the system. And from these images, you can see that the amount of time a water mass stays in place varies from one day in that shallow plume to over a year in the deep waters around Harrow Strait. The nutrients that are being delivered through this circulation drive primary production in the system. Productivity is high relative to other temperate estuarine systems here because we have this rich array of nutrients coming in. This primary production includes things like phytoplankton, but also benthic plankton, seagrasses, kelps, and other microalgae that many of you probably know about and work on yourselves. Primary productivity is a biochemical process, primarily photosynthesis, that converts the sun's energy into food for the entire ecosystem. And this primary production supports an entire food web. The illustration on the left represents a simplified version of this food web, going from the phytoplankton up to zooplankton and forage fishes and so on. But it's important to understand that scientists in the Salish Sea are quantifying this food web using a variety of models to better understand energy flow through the system and changes to the fundamental structure of the ecosystem over time. In addition, we have a number of critical habitats beneath the surface. These numerous habitats provide ecosystem services to the people in our region. While some of these biogenic habitats like kelp and eelgrass are well-known features of estuarine ecosystems, others like glass sponges are still being documented but play an important role in carbon sequestration, and still others like the Olympia oyster are being renewed after periods of overharvest and decline. All of these biogenic habitats are critically important in maintaining ecosystem function, from biogeochemical cycling to habitat provisioning for fishes and invertebrates. And this high productivity and mosaic of habitats resulting from nutrient-rich ocean waters and circulation supports many of the enchanting species that rely on the Salish Sea ecosystem as their home. But we know this habitat is being threatened. Throughout the watersheds and within the estuarine seascape, we're seeing the effects of this. In this report, we've tackled two primary causes of concern: urbanization and climate change. Urbanization is inherently local, while climate change is global in scope, but has real implications locally in our ecosystem. The confluence of these two major stressors brings with it a new set of challenges entirely. We are an urbanized and urbanizing estuary with the sprawling metropolises of Vancouver and Seattle and other sizable cities like Victoria, Olympia, and Tacoma. The infrastructure we have built to support our commerce and economic engines has come at the expense of natural habitats and has disrupted ecosystem structures and function. Much of this development actually occurred a long time ago, with retrofits and additions over time. So here in Bellingham, the waterfront was largely built out by the early 1900s, with much wetland and marine shoreline lost to industries like canneries, mills, and other operations that were taking advantage of our robust natural resources. Similarly, the railroad running the length of the east side of the Salish Sea from Olympia to north of Vancouver has been in place for over 100 years, disrupting shoreline processes and separating uplands from the estuary, reducing natural sediment supply and the transition zone between the estuarine and upland ecosystems. Much of what was transition habitat, marsh and delta specifically, has been filled for urban development and agriculture. Meanwhile, the Salish Sea, in addition to being the recipient of much freshwater input, is also the recipient of a vast array of contaminants resulting from human activities. This complex contaminant mixture, pictured in this cartoon from USGS, can lead to lethal and sublethal effects in biota through long-term multi-generational exposures and with linkages across trophic levels. We have taken action and we continue to take action. We're educating people about stormwater. You'll hear a little bit more about that in a bit. Municipalities are improving infrastructure, and legacy impacts are being remedied by concerned community members, dedicated NGOs, and governments to remove hazards and protect and restore the Salish Sea. Many urbanization problems can be solved with by understanding the root problem and garnering the political will and concomitant funding to make change. Watershed protection, treatment of stormwater runoff, shoreline buffers, and other technological or regulatory actions can be implemented right now to move the needle toward lessening human impact. But the fact remains we are a very populous region. The local impacts from human growth and infrastructure and the impacts to the seascape are now combined with climate change in local manifestations of a global problem to which we are all contributing. 2020 was one of the warmest years on record. 2016 remains the record, with much of the globe up to 2 degrees above average and some areas exceeding 4 degrees Celsius above normal. And temperatures are continuing to climb. I just looked at some local news articles from the past couple of weeks. And while we've had a fairly cool start to 2021, conditions in the region for this summer are projected to again be hot and dry, fitting with recent trends in the direction of both. So global change is being expressed in local impacts. We have very active and productive groups in our region in the Pacific Climate Impacts Consortium at UVic and the Climate Impacts Group at the University of Washington that are both taking global climate models and applying them to regional analyses to better understand local impacts. These are largely looking at physical processes, so using downscaled climate models with climate model inputs to make predictions about how processes like stream flow or sea surface temperature might change within the Salish Sea. They're also using model inputs, we can get some information, but there are also events like the marine heat wave known as the blob, which serve as natural experiments to provide observations we can use as inputs to validate our model predictions, but also see how our system responds during these short-term events. Here we see that the marine heat wave known as the blob resulted in temperatures throughout the North Pacific of 1 to 3 degrees above normal, including in parts of the Salish Sea. I think this image shows the connectivity between the Pacific Ocean and the Salish Sea. We are directly influenced by changes to water temperatures within the Pacific Ocean. So this portends the rate of change in sea surface temperature that we expect to see from global climate change, which is predicted to be between 1 and 3 degrees C. This warming is having profound effects on our ocean, with thermal expansion of water masses leading to greater volumes of water, which interact with our coastal infrastructure in ways we did not anticipate when it was constructed. In this way, global climate change is having local impacts. The sea is rising, inundating low-lying areas and changing the shallow intertidal zone. Tribes and First Nations are doing some of the leading work to document these impacts and develop climate adaptation plans in response, as their lands are most vulnerable to this impact. We know that the physical effects of climate change are influencing the Salish Sea. Acidification and deoxygenation are anomalously high in this region due to our coastal oceanography, and we know that water temperatures and sea levels are rising. But due to the complex oceanography, that circulation that I mentioned previously, and the large size of this ecosystem, conclusive studies about biological response are still in the works, although there are many papers out there now. Cataloging of impacts from phytoplankton through top predators like birds, fishes, and mammals is ongoing. Some examples that we can speak to today include work on eelgrass and sea stars that has shown that increasing water temperatures increase susceptibility to disease. And increasing ocean acidification has effects on numerous calcifying organisms. We must also consider that non-climate anthropogenic stressors, those caused by humans but not climate related, affect the capacity of biota to adapt to climate change, potentially worsening conditions and adaptability of many species. And this is an area of rich research going on now. So that brings us to this idea of cumulative ecosystem effects. We might think about these altered ecosystems being impacted by both urbanization and climate change. We often depict these cumulative effects with cartoons because in reality, they're actually quite difficult to study and to get a handle on. But we've made some great strides in some areas, like observing and documenting the impacts of shoreline armoring, shown here by work from Megan Detier. And on a more global scale, we've also seen the impacts of anthropogenic noise in this recent paper from Duarte et al. And our region is no different from what is shown here, I guess in reverse form. I'm not quite sure what happened there. Our permitting processes are often piecemeal, parcel by parcel, impact by impact. So having evidence of large scale cumulative impacts provides rationale to take larger scale policy action to prevent further degradation. So the idea of documenting these cumulative impacts of many different stressors is crucial to understanding how we can move forward to prevent these things. So I've done a fair bit of work on salmon marine survival over the last couple of years, and there are a number of studies that have shown that salmon within the Salish Sea, specifically coho and chinook, have suffered increased mortality or reduced survival relative to those from coastal stocks. These studies all showed declining marine survival, but with different groupings and coherence at different scales. A large project is just wrapping up about the marine survival of salmon in this region. And I wanted to say that one of the things that has come to the fore for me with this project is really thinking about salmon as ecosystem integrators. They're moving from our headwater streams out through the Salish Sea and the ocean. And they're subject to all of the conditions along the way, including whatever they are experiencing in the Salish Sea during an important early marine life history. In short, the pressures are relentless and growing as legacy continuing and emerging impacts converge. So given all this, the final sections of the report offer some insights into possible actions that could be taken to remedy harms and prevent further declines. I'm going to walk through them now. This slide is not the most easy to read, but we've grouped these into 3 broad categories, each with subcategories that I will walk through in the next few slides. So the 3 categories are to build habits and support for collaborating across disciplines and borders, strengthen the science to management bridge, and embrace multiple ways of knowing. So in each of these subgroups, we've come up with a number of ways that we feel that the science can be advanced through various efforts in the Salish Sea. This first one is to advance data collection and monitoring using novel tools. And I mention this because there are vast data collection efforts in the Salish Sea, but we're starting to get to the point with remotely sensed data that we can accumulate an awful lot of data in a short period of time. But maintaining these time series is critical to detecting change over time. We have a really strong modeling community in this ecosystem as well. There are a number of groups focusing on different aspects of the ecosystem, physical properties, biological properties, and using these models as integrative tools is really critical to take the data that we've collected and build these models to a more integrative purpose. Of course, there's an old saying in modeling that the model is only as good as the data that go into it. And so making sure that we are getting quality data from throughout the Salish Sea is really important to building these integrated models and making sure that they work. So in an age of open data and open science and lots of advancement in that front, especially within my field of environmental science, the need to create a transboundary Salish Sea data and information repository is high. The Strait of Georgia Data Center also serves as a repository for data on the north side of the border, but this could be broadened to include more data from throughout the Salish Sea ecosystem. The last suggestion under this group is to establish a Salish Sea science panel to set an overall Salish Sea science agenda for the region. The next topic is to embrace multiple ways of knowing. So throughout this report, we've worked with tribes and First Nations to recognize some of the contributions that their communities are making to science in the Salish Sea. So it's really important to recognize these knowledge systems as we move forward and integrate them into what I refer to as an overall social ecological system science for the Salish Sea. And there are groups doing this, Social Science for the Salish Sea, and many others are focusing on this aspect. It's really important we consider both the humans and the ecosystem within this, if we intend to make progress in this region. Also, building knowledge, relationships, and connection through place-based education. At the top of the hour, Ginny talked about the Salish Sea Minor here at Western Washington University. There are other programs at other universities that are capitalizing on this place that we call home to build knowledge and understanding of the region. This engenders some sort of collective knowledge among the future generations and fosters connection between the ecosystem with the people living here. Lastly, this is in the science to management category. So strengthening this bridge where we're taking the quality science that we have in this region and really translating it to policy actions is important. And we have a few suggestions here. So the first is to enable practitioners to bridge this science community and community investment. There are a lot of really active, engaged people in this region, judging by the number of people who have signed up for this presentation, who really want to engage. And I think making it possible, more possible to engage these people, interested parties on a broader basis is important to this idea of strengthening the science to management bridge. Using adaptive management tools to strengthen planning is another one. This is not a new idea. In fact, it's been around in this region for a long time, started by a group out of UBC, including Carl Walters. The last one is to build sustained and regenerative ecosystem functions to improve resilience. So we know we can't go back to the ecosystem as it was previously, but we can make regenerative ecosystem, novel habitats and other things that return some function to engender resilience in our system. There are exciting new frontiers in data collection, model integration and understanding how that data can be put together to understand processes and functions in the Salish Sea, and new thinking about using traditional ways of knowing to improve management. All of these offer hope and exciting opportunities for the future. Science is critical for understanding fundamental processes and change, but it's not the answer in and of itself. Communication and connection are key for bringing awareness and expertise to problems, and our leadership must be bold to protect and restore this ecosystem given cumulative changes. So I leave you with this question. Can agencies, organizations, and people acknowledge the Salish Sea as a shared ecosystem to shape their work ahead? Thank you.
Thank you so much, Kathryn. Clearly, it's going to take all of us, and it's not just about the science, but the science is really important as our base here and where we're going to focus today. We are going to do some questions, but we're going to wait until all the speakers have a chance to talk, and I'll refer you to the Q&A box to put your questions in there. I'd like to introduce Emily Howe. And I really want to thank Emily for coming at a little bit short notice. We had anticipated having Tara Martin from UBC come and share with us about the Fraser River, and we hope to have her for another symposium in the future, but she had a conflict that happened, and Emily is here to talk to us about stormwater. I haven't met Emily, and that reminds me that there's a lot of us who haven't had a chance to see each other during the last year. So I hope to get to meet you in person, Emily. She works as an aquatic ecologist at the Nature Conservancy. Her PhD is from University of Washington with a focus on estuarine restoration and food web ecology and tidally influenced ecosystems. She's a very good fit here with us. She says she's comfortable working at the nexus of stormwater pollution, green infrastructure, and restoration ecology, which is very fitting. She is the author of vignette number 7 in the report on stormwater, and she's going to talk to us now. So I'll turn it over to you, Emily. Thank you.
Hey everyone, it's good to be here today. Let me get my slides up for you. Yeah, so I am an estuarine and aquatic ecologist for the Nature Conservancy. And I actually want to, I'm speaking from Seattle, the homelands of the Duwamish people. And I also owe a thank you to Kathryn, who actually was the one who turned around, opened the door, and pulled me in as a young scientist when I graduated from college. So she's credited with my entrance into being a Salish Sea ecosystem researcher. So yeah, I contributed a vignette on stormwater, and stormwater is actually surface water runoff that is generated by rain, not just storms, but even drizzle events, anything that can actually create water flowing across the surface of the land. And it's one of the fastest growing sources of water pollution in the United States. And there are over 10 trillion gallons of untreated stormwater that flow off urban surfaces every single year into the nation's waterways. And although it is a federally regulated source of pollution, it's chronically underfunded, and there are over 700 cities that are currently facing legal action by the EPA because they are out of compliance with Clean Water Act standards. It's also a really expensive thing to deal with. So most of our urban infrastructure is aging and requires a fix. For the most part, it wasn't ever meant to handle the flows that we experience today. As we have increasing impervious surface across the landscape, we get more flow. And also that infrastructure was never really meant to clean the water in the first place. Stormwater wasn't really viewed as sort of a dirty thing in the very, 100 years ago or so. But what we know is that the reason it is the fastest growing source of pollution or water pollution is because it's related to population expansion and development expansion. And so here we're looking at sort of the Puget Sound region of the Salish Sea. The red is the amount of impervious surface. And you can see from the 1960s to the mid-2000s, there is a pretty large expansion in the amount of impervious surface. So more pavement begets more runoff. You add climate change on top of that, you have more intense rainfall. So now we actually have rainfall or surface runoff that is about 1,000% of historical conditions. And that creates the twin problems of stormwater, which is more flooding. So we have a flow quantity problem and more pollution. So this is a water quality issue. And there's a really robust and deep body of scientific literature describing the detrimental impacts of stormwater on marine and aquatic species. As Kathryn mentioned, some of those impacts are acutely lethal, and this is the case for coho salmon. So these are anadromous fish species, right? They are born in freshwater. They migrate out to the marine ecosystem where they grow, and then they return back to their natal streams to lay eggs. And the fish that come back to very urban creeks experience something called pre-spawn mortality. So they die, they basically suffocate on the spawning grounds with their bellies still full of eggs. And the pre-spawn mortality rates are much higher in urbanized watersheds compared to outlying areas. In addition to those very acute lethal impacts that are displayed by coho salmon in response to stormwater, we also have sublethal effects. So this is caused by the accumulation or the long-term exposure or the bioaccumulation of things like persistent organic pollutants like PCBs and flame retardants. These kinds of chemicals can travel across space in the bodies of organisms, and they can travel up trophic levels to top level predators like orcas. And in the case of orcas, when you combine that bioaccumulation with toxics with famine conditions, they begin to metabolize their own body fats. And this releases those toxics into their bodies that were formerly bound up in the fat. And this suppresses their reproductive health, contributes to failed pregnancies, and of course, then population declines. So we have very severe documented impacts on native species as a result of stormwater. But we also know we have thousands of chemicals running off of streets and roofs. We have trillions of liters of water to deal with. And so we often ask the question, well, what can we do? So in addition to source control for particularly pernicious chemicals, one thing that's come and risen up as a solution is the use of green infrastructure across our urbanizing landscapes. So green infrastructure is often the most cost-effective option in filtering and cleaning polluted runoff. And this can come in the form of bioswales or rain gardens, but also the preservation of green space and tree canopy. But this still remains, the question is, like, so now maybe we know what to do, but how much of it do we need and where on earth do we put it? So this is what brings me to the 4 vignettes I want to present to you today. So this work represents about 5 years of work that the Nature Conservancy has been involved with. This represents a group of colleagues at the NOAA Northwest District Science Center and also Phil Levin's lab at the University of Washington. So the first two pieces are focused on, can we even map where this pollution is located and where it's coming from on the landscape? So there's two pieces about how might we predict pollution loading across the watershed. And the second two get into thought exercises on how might we begin to prioritize where to work. So starting with something called the Stormwater Heat Map. This is a tool that we've been building at the Nature Conservancy to help stormwater planners prioritize areas and watersheds for stormwater improvements. It is still in construction. We're hoping to release it by the end of June. We'll see if we make that cut. But anyways, the Nature Conservancy began building this because the Department of Ecology a few years back announced that in addition to the phase 1 cities and counties that are required to create science-based stormwater management plans, they were going to start requiring the phase 2 cities and counties to also create those plans. These plans are expensive to create. They're $1 to $2 million projects. They have a lot of hydrological modeling and they require technical expertise. So what we know about these phase 2 cities and counties is that there's 85 of them or so within the Puget Sound region of the Salish Sea. And they often have a stormwater department of 1 or 0, and they lack a lot of funding. So we would rather that they put that funding towards implementation rather towards the planning. And the Nature Conservancy felt like there was a possibility to help buy down that cost of planning through the development of a tool. So we embarked on a design thinking exercise whereby we interviewed stormwater managers and planners and modelers throughout the region to figure out what a useful tool might look like and what it might contain. And design thinking is a structured methodology that's used to elicit human patterns, people's pain points, people's constraints, but also their aspirations. And what we heard as a result of that exercise was that a really useful tool could do a couple of things. Number one, it had to have extremely compelling visuals that told the stormwater story, and it needed to operate at multiple scales. So you need to be zooming all the way into the parcel scale and all the way out to the regional scale and everything in between. In addition to that, the thing needed to be completely mineable. So all the data needed to be exportable and transparent and usable with other tools. And finally, it needed to be grounded in science, it needed to be transparent, and it needed to use best practices. So that's what we set out to build. The thing involves a couple of components. There's a high resolution land cover layer. This gets folded into the hydrology modeling. Those two things then get combined with pollution monitoring data from those phase 1 cities and counties to calculate a pollution loading metric. And then that all goes into an interactive tool. And we're kind of still working on these two things. So the land cover data set required a pile of different data sources and machine learning algorithms to get down to this 1 meter square resolution, which is what's useful at the parcel scale when you're thinking about stormwater. You got to know how much water is running off every, a sidewalk or compared to a roadway, because they have different pollution loads. This land cover layer was then folded into what are called hydrologic response units. So water percolates and runs off land differently depending on the land cover type, the slope, and the type of soil. So for all 30 hydrologic response units, at all 311 precipitation grid cells, for 4 different epochs, at 33,000 time steps, we have flow runoff data. And you can get it at Google's BigQuery database. So all that data is then combined with pollution concentration data from the Department of Ecology, and we're in the process of creating these predictive models based on landscape characteristics for a suite of different stormwater pollutants. And the upshot will be a tool that looks something like this. So it's a heat map that tells you where is stormwater being, where are the pollutants in stormwater being generated on the landscape? And can we then use those hotspots as places to put green infrastructure, for example? And this thing is something that you can look at the regional level, but you can zoom all the way into the parcel level. And here you can see I-5 running along the shores of Lake Union as a particularly rough hotspot for zinc here. Most of these data, when we began building the tool, were based on kind of static data, static landscape characteristics, in addition to precipitation, which is more dynamic. So Phil Levin's lab took up our question about, what about dynamic traffic data? We know that braking and acceleration and speed and curves and idling, that all of that plays into how much pollution is created by a vehicle on a roadway. So don't we need to incorporate that dynamic nature of traffic while we're thinking about the stormwater heat map? So Mathis Messager and Ian Davies asked the question, well, can we predict pollution hotspots using traffic volume and behavior? So what they did is they basically took, your handheld device traffic maps. So these are Bing traffic maps. They kind of show you where traffic is red versus yellow and green, which tells you about how slow or congested traffic is. So they basically scraped that visual data, turned it into traffic volume and behavior data, and then combined that with observational data of pollutants. So what they did is they used this cool X-ray gun, which they zapped moss from different areas throughout the region that represent different amounts of traffic. And they were able to create an observational database of the concentration of these 3 heavy metals throughout the Puget Sound zone. They were able to use these as training data for their predictive models. And as a result, they created these fabulous high resolution maps of heavy metal loading throughout the Puget Sound Salish Sea watershed. And one of their key findings was that 50% of that total pollution for these 3 metals is deposited on only 3.3% of the land area. So it helps us concentrate our focus on where to work. But it also told us that getting that traffic data and the dynamic behavior within it was really important for that heat map. People don't like to give you their traffic data. It's a very closely held type of data, but we were able to purchase it finally. But it was costly, but it was worth it. And Matisse and Ian's paper showed us why. But even these maps, so we think of these maps as sort of the threatscape, but we need to, in order to figure out where to work, we still have to connect it to the species themselves. We have to prioritize where we work based on what organisms we're interested in and what their life histories are. So kind of where they go and where they're vulnerable. So this brings us to some work that was led by Eileen Ettinger, who's a quantitative ecologist at the Nature Conservancy, but also a team of colleagues from NOAA's Northwest Fisheries Science Center. So remember when we were talking about coho, they had that predicted pre-spawn mortality map that was related to an urbanization gradient. So some areas had higher levels of pre-spawn mortality than others. And so this team was able to use that urbanization gradient and the amount of pre-spawn mortality to identify a threshold above which coho do fine. Their population is stable or growing. And below that threshold, coho do not do fine. The mortality pressure is too high from stormwater and their population begins to go down. And they can relate that to a certain degree of urbanization. So they built this framework around that. On one side, you have preservation. So preservation is implemented to prevent increased urbanization effects that would push these fish towards that threshold. And then there's restoration that would reduce urbanization effects. And so that would flop you back over that threshold into the positive growth rate period. And so the highest priority areas where you can do the least amount of work are right around that threshold. So they turn this framework into spatial maps. And here's what the map looks like for coho prioritization. So this would tell you, if you're interested in coho conservation, where would you do restoration, like bioswales and stuff, and where would you do preservation, like the purchasing of green space. But the thing is, the coho maps are quite different than the Chinook maps. This is because these fish are vulnerable to different life stages and they utilize different parts of the river systems. So while a framework like this, scientists can provide answers, it's really critical that we all work together to identify the objectives. The objectives have to be clear in order to have a usable answer. And this brings us to the fourth vignette here, which is thinking about how do we match the scales of our management objectives to the scales of the solutions. So we started thinking about coho, Chinook, and southern resident killer whales that all have very different ranges, right? So southern resident killer whales forage along all of this turquoise area from Haida Gwaii to Point Conception in California, Chinook from the Sacramento River up in the Gulf of Alaska. And the thing that these all have in common is the Northern California current system. So what is the pollution loading to the Northern California current system? And where do we go from there? So we quantified the amount of impervious surface area, and we quantified the total amount of pollution loading or stormwater runoff. And we found that by addressing to address 70% of the pollution loading, you only got to address 1.3% of the land area. And that pollution is generated in 4 main areas. The Seattle metro region, Portland, San Francisco, and Sacramento. We didn't have data for the Canadian side of the Salish Sea, so I would add in Vancouver, Victoria, probably other major areas to think about. But as we think about this thought exercise, this means that for coho, which use small tributaries, all these yellow dots, that you can get away with uncoordinated management in small watersheds and do pretty well at coho conservation. When you start moving into Chinook, these guys use main stem rivers and they use estuaries. And so now they're dealing with the cumulative effects of watershed loading. So now you need to have coordination among stormwater managers within an entire watershed. But by the time you get to orcas, now you got to think about the entire foraging range of the species, which range from the mouth of the San Francisco Bay all the way up to the Salish Sea. And so this is a classic example of a scale mismatch. So stormwater in the United States is managed on these very small stormwater jurisdictions called MS4, and you have your organisms that are operating at these very large ecosystem scales. And so to be successful in our strategic objectives in the case of native species and stormwater, we're going to need some scale crossing brokers who can implement policies to effectively bridge different scales of governance, everything from that very small MS4 stormwater jurisdiction to the interstate and international agreements. So that's what I've got about stormwater. And I'm really excited to be here with all of you today. Thanks.
Thank you so much, Emily. I wonder if just a quick question of whether similar work has been done in the Vancouver, British Columbia area, as you just were showing for Seattle and Puget Sound.
Not that I personally know of, but for the Canadians on the webinar today, I would be more than happy to hear from you and to hear what data sources are available so that we could expand this tool that direction.
Awesome, thank you. Okay, well, I'm going to introduce our next speaker. Aquila Flower. Aquila is a trained geographer. She works at Western Washington University also. Her research focuses on the role of climatic variability, human land use patterns, and natural disturbances in shaping forest, alpine, and coastal ecosystem dynamics. From my observations, she has an absolute passion for making maps of the Salish Sea and apparently amazing patience figuring out how to make them, because it is no easy task with the data being different on both sides of the border. The State of the Salish Sea report debuts a series of Aquila's new maps showing different data layers. They are a really important step towards our ability to see the Salish Sea holistically. So thank you for being with us, Aquila. It's all yours.
Thank you. It is such an honor to be here, part of this presentation. Let me get my slides up. Okay. As Ginny said, I really do climatology and forest ecology work more than mapping science when it comes to my research. But working and living in this transboundary region for a number of years, I have run into so many annoyances with the lack of cohesive spatial data sets and maps going across the border that finally I just had to start doing something about it. So I was delighted to be able to be part of this report, and I'm also working on a larger atlas project trying to create more data sets in which I'm mapping the Salish Sea. So I want to start with this figure here, showing the location of the Salish Sea watershed within the context of the large watersheds of North America. So you can see our big neighbors, the Mackenzie and Columbia watersheds, and then the watersheds that feed into the Salish Sea from the Fraser River and the smaller coastal Pacific watersheds. Those watersheds, through their streams and rivers, connect these land areas with the Salish Sea and then with the Pacific Ocean that of course we're connected with, but also somewhat sheltered from. So I'm an associate professor of geography in the sort of central Salish Sea in Bellingham at Western Washington University on the ancestral homelands of the Lummi and Nooksack people. I'm delighted to live here in this beautiful part of the world and honored to get to make maps of it. Okay, so transboundary mapping is wonderful and powerful. It's very important for our science, our outreach, and management decisions to have compelling maps and accurate data sets that comprehensively cover the whole region. When you're talking about a transboundary region, you need data and maps that go across the whole region. But getting those data and making those maps is often very challenging. My presentation today is going to be a bit of complaining about those difficulties, but hopefully inspiring ways that we can make this easier for people doing this sort of work in the future. So my work related to Salish Sea mapping involves making reference maps like this one shown here. This is an updated reference map using kind of higher resolution bathymetry and elevation data than we've had in the past. Just as a basic reference map so we can all talk about the Salish Sea region and know what we're talking about. And I made a number of maps for the State of the Salish Sea report. And as I mentioned, I'm working on a comprehensive Salish Sea atlas. I'll talk about that a little bit at the end. So I want to jump into some of the challenges. I'm going to show the maps that I made for the State of the Salish Sea report. One by one, you saw some of those in Kathryn's presentation, but I'll show them again as I go through and talk about some of the challenges that I face and that any researcher trying to work with spatial data in this region would face. So this first one is the simplest of maps. This is just US counties and Canadian regional districts, just to kind of show the jurisdictions, who's in charge of this land. But even one like this requires some decisions about what your study area is. Where is this region that we're talking about? And it turns out that defining regions and your basic terminology can be pretty challenging, especially working in an international context. I have this definition of the region that I used in my maps for this report and in my atlas, but it's not the same definition that everyone has used. Ginny showed before Stefan Freeland's iconic and beautiful map of the Salish Sea, and the boundary he used is slightly different. We use different definitions, and so people keep asking me about that. I want to point out there are lots of different definitions that are used. Here are some maps that I found just doing a Google image search, coming from reputable locations, and don't get into the details of it, but notice that the shape is different. People are defining this region differently. So when we talk about the Salish Sea, we might not all be talking about the same thing. So that's just step one in mapping this area, is figuring out what this area is. Part of that is related to legal definitions versus informal definitions of what the Salish Sea is, and also the fact that there are different definitions for the US and for Canada of something like the Salish Sea, or any other transboundary region might have differences like this. So I have little definitions up here from the US Board on Geographic Names. Says, well, how far north does the Salish Sea go? It goes northward to include Puget Sound, Georgia Strait, and their associated bays, coves, and inlets, which kind of amuses me because there are a lot of bays, coves, and inlets. I need more specificity than that. But then BC geographical names gets into a little more detail. It says that the northern boundary goes just beyond the Strait of Georgia to include the channels and waterways where the flood stream or tidal surges from the south. Okay, so now we're getting into a little bit of oceanography. This starts to make sense as how you would define the borders, right? We want to think about where we're having an exchange of water in and out of the Salish Sea. So that's a lot of detail, but it's just one of those basic things I had to do at the beginning. This map over here from the report shows subbasins and bathymetry of the Salish Sea. And defining each of these subbasins required decisions along the way. I wanted as much as possible to use definitions that were used commonly by government agencies, and if possible, had a legal backing for the definition. So we have US subbasins commonly used by USGS, and primarily Canadian subbasins used in the BC Freshwater Atlas, but I had to make some adjustments. So this is a big challenge. If you're working with any data sets, often you'll find that data are aggregated for instance, a subbasin, the Strait of Juan de Fuca. Is it split into west and east, or is it one big entity? That makes it difficult to map or analyze any of these variables we might be interested in because we're defining our study areas differently. None of these definitions are necessarily right or wrong. They're just different definitions, and we have to be really clear about which ones we're using. And if possible, coming up with standards that everyone uses would be ideal. Okay, thinking about the oceanographic inputs into the definition of our region brings us to this next figure that Kathryn and I spent quite a bit of time working on, trying to integrate data from different sources to summarize in a simple way what is happening with the exchange of both the deeper marine waters that come into the Salish Sea and the more brackish water going out with fresh water from the rivers in our region. This figure points out just the big take-home message is that the vast majority, about 95% of the exchange of water coming in and out of the Salish Sea is going through the Strait of Juan de Fuca, not through the northern passageways. And so that explains the definition of where that northern boundary of the Salish Sea is. But that's not at all obvious to us as terrestrial organisms who are used to looking at 2D maps. We simply don't have knowledge of what's going on under the water necessarily. And so it might not make sense to us at first when we look at these maps. This brings up one of the other data challenges, definitely with transboundary mapping, is simply what do we know? What do we have adequate data for? So for instance, working with mapping circulation in this region, there's a lot that we still don't really know, and different data sets kind of give you different answers for different times. There are many data sets that we are still lacking. We never got to make the map of kelp that we wanted for this report because there simply isn't a comprehensive kelp survey. So a big challenge in this region is just which data sets do actually exist comprehensively for the entire region. All right, another map here. This shows human population density. So this is people per square kilometer. This is for 2010 in the US and 2011 in Canada. And this map gives me the most to complain about, the most challenges to discuss, I think. Census data is a good example of what should be simple. You think, well, we have a Canadian census record and a US census record. We just combine them and know where people live, right? But it turns out to be much trickier than that. When we're taking any two data sets from the US and Canada or across any borders like that, we find that the data sets might not necessarily line up spatially. So in fact, with the census data, it surprises me that you'd think they would have accurate international borders, but there are gaps and overlaps in between the data sets along the border. The scale of different data sets might not be the same, and the level of generalization might not be the same. That's a big problem working with features like rivers, where you might have a very detailed line representing the river, or a much more generalized line. And to combine two data sets with different levels of generalization, you might not come up with something meaningful or useful. Different levels of aggregation. Census data is a good example of this, but many variables are aggregated within some larger area. So US and Canada use different definitions of what they aggregate census data within: blocks, tracts, subdivisions, and so on. Making those comparable is sometimes impossible, but often at least difficult. We might have differences in coordinate systems, defining our boundaries, and then we might have temporal mismatches. When and how often are our data collected? The US and Canadian censuses happen in different years at different frequencies, and that makes it challenging to create a comprehensive data set. And that's not just a problem with census data. Certainly many ecological surveys happen in different years, and you have to decide how close in time do those data sets need to be to each other before they can be combined and be useful. Then there are the bigger issues of conceptual mismatches. Simple things like units of measurement, but bigger things like how were the data collected? Was it, for the census data, was it a true census where everyone answers, or was it a survey? And then how do we conceptualize the data? How do we categorize or create scales for the data? If we want to look at census records of education, are we looking at education of people, educational attainment of people over 18 or over 25? If we're looking at race and ethnicity, we see totally different categories used in some cases in Canada and the US. Looking at ecology, if we're looking at different forest types, the definitions of the forest ecosystems are similar, but not directly comparable in Canada and the US. So all of those variables need to be harmonized somehow so that you can map out a comprehensive, cohesive story for the region. But let's say we do that, then we can look at these interesting maps like human population density that I was showing, and very related to it, our land cover map on the right. This land cover map shows gray areas, gray for urban areas, yellow for agriculture, and then green for our vegetated areas. Both of these tell a striking story of how concentrated human population is within the Salish Sea bioregion. That green area on the population density map that represents less than 1 person per square kilometer takes up 70% of the land area of this region. So there's a big area of our Salish Sea bioregion, as I'm defining it, the watersheds of the Salish Sea, that doesn't have a lot of people living in it. Yet we have really pervasive human impacts happening in those areas. And logging, mining, very pervasive climate change effects. All of these things are, of course, affecting the Salish Sea itself, even though they might be happening remotely from human populations. One of the big ways that they connect to and affect the Salish Sea are through moving through streams. So mapping the rivers is, of course, very important for this region. This map is one that Kathryn showed as well. It has the 12 highest volume rivers for our region. The Fraser River, of course, stands out. It represents more than half of the freshwater inflow into the Salish Sea. But this figure here draws on several decades of records from Canadian and US sources to create a single comprehensive visualization of where we're getting our freshwater inputs from. Okay, so those are a few maps from the report and a few challenges that we ran into. I see this as a place where there's a lot of opportunity to improve transboundary mapping and any sort of analysis that's happening in this region. It should not be as difficult to do what I did as it was, right? We should just have easy data sets that we can all access. So I think it should be a priority in our region for so many issues that require spatial data to have cohesive, comprehensive, and easily accessible data sets for spatial analysts to use, for cartographers to use, for any scientist to use. We also need to have visualizations of these data, free and open access maps and other summaries of the spatial data that could be used by educators and policymakers and any community member to understand these spatial patterns and processes. All of this requires international collaboration to develop data standards, so we're measuring the same things in the same way, to disseminate the data sets easily and freely, and to prioritize data collection efforts. So I wanted to give a little pitch for my forthcoming Salish Sea Atlas that's going to take a little stab at part of this. This is going to be supported by the Salish Sea Institute. And this is going to be an atlas focused on just the comprehensive data sets describing basic characteristics of the Salish Sea bioregion. So there's a website up with some early products in it. I just have a couple of chapters out, but you can download the reference maps like I showed at the beginning, download any of the data sets that I have shared publicly. So for instance, an elevation data set or a data set of the rivers in our region, and look at different atlas chapters. This will let you interact more dynamically with the data sets instead of just looking at a static map. You could explore a map like this through the Salish Sea Atlas online that shows a Salish Sea estimated population in 2019. You can click around on any of the different, these are counties and regional districts, and access details about that specific location. This one is showing population change over time on a graph, and you have a detailed table. And all the data sets will be downloadable, so you can make your own maps and do your own analysis. It's also basic things like, where's Rosario Strait? You want to know the location of different water bodies or islands. It's easy to click around on these maps. And maybe you want to explore where your home lies in terms of the linguistic regions of the Coast Salish peoples. That's one of the maps that's in there too. So please keep an eye on that. This is going to be a companion product to the State of the Salish Sea report. Okay, with that, I'll just say thank you, and note again what a joy it has been to work with Kathryn and Ginny and Natalie on this project. It has been a really wonderful team, and again, an honor to be able to contribute to this report. Okay, thank you.
Thank you so much, Aquila. And just to confirm that your maps are available for use freely, as long as they're properly referenced for you. Yes,
that's right. Yes, all the reports in the, all the maps in the report are open access.
Awesome, thank you. It really feels like a game changer to have all of these maps available. And I want to just acknowledge, I mean, obviously Aquila was talking about the barriers in terms of data harmonization and the different ways that data are collected. And I just want to state, you know, the obvious too, is that agencies have jurisdictions, right? And agencies can only spend money within their jurisdiction. And so there's these natural barriers to addressing Salish Sea issues and monitoring cohesively and collaboratively. So some of this stuff is spelled out in the State of the Salish Sea report. And also we provide, I think, some opportunities to work around some of these things and getting people to collaborate more and think outside their borders. I want to invite all of our speakers to come on, turn your video on. Hello. There are a bunch of questions, and I know there's a lot of answering of questions going on in the Q&A spot, so speakers can feel free to pick some of those off. Kathryn, I want to raise a question to you that came in about the blob and why there is a difference in the heat from the blob on the east side of Vancouver Island than the west side.
I saw this question, and there are a few people on this call that can probably do a much better job than I can at explaining this, but I think it has to do with our underlying oceanography, things like upwelling and various other oceanographic phenomena that are happening and changing the way that water temperature will manifest at the surface. And I actually did pull the paper up and to see if it was, I can't remember if the figure is surface water or some sort of integrated measurement, but I can pass that along to the person that asked the question. So, and provide a little bit more information.
Awesome. Okay. Here's, I'm going to read from some that came in during the original registration process. There's a question about outdated sewage treatment plants around the Salish Sea being a major source of pollution. Does anybody have, we're not quite sure who might address that, either Emily or Kathryn, is that in your wheelhouse? Outdated sewage treatment.
I know
that one.
that, right, that there's been a lot of work trying to trace, particularly for nutrients, is the source, largely coming from, wastewater versus stormwater versus just runoff. And yeah, the sewage plants definitely are contributing quite a bit of nutrients to the system. I can't speak to whether they're outdated or not, but we do know that there are a number of different chemicals of emerging concern, basically in the pharmaceutical range, that are being identified as they are not being cleaned, basically, or captured through our current wastewater treatment. And so a lot of these types of chemicals are endocrine disruptors, so they really mess with the reproductive success of marine and freshwater species. But I would be speaking far outside my field if I went too much further than that.
Okay, fair enough. Here's another question from a, let's see, okay, sorry, my eyes are jumping all around because there's so many here that are good ones. How well do the issues that beset the Salish Sea represent key issues facing other marginal seas around the world's oceans? This is probably another one that isn't necessarily in anybody's wheelhouse because it's more of a global question, but maybe stated it differently. I mean, to me, the issues that we're facing from global climate change and, normal human development, this is typical of other areas. It's happening globally. Kathryn, do you have something to share that might really speak to how the Salish Sea is addressing this in a different fashion?
Yeah, I can chime in a little bit. I did my PhD work in Chesapeake Bay, which is another estuary that actually has a wealth of data that's been collected over the years there. Many of the issues are the same, but the manifestations of the problems are very different given the oceanography that we have in this region. There are other ecosystems like the Bering Sea, for example, that does not have our population, but is really suffering effects of global climate change. So how these things interact is somewhat unique in these different coastal ecosystems. It really just depends on what the history. San Francisco Bay is yet different again, and Emily can probably speak about a paper she was just involved with about deficits and primary production there caused by human impacts. So I think a lot of the issues are the same, but how they manifest is very different. So I'll leave it there for now.
Okay. Here's one that I think anybody could take a stab at. How can the non-science community use and more deeply understand the contents of this report? Maybe that's mine. What are we going to do to translate this information? We do have an executive summary. It's short, and to be fair, it certainly, it doesn't tell the full story. But maybe that's a challenge for all of us to be continue to be working on sharing symposia with a variety of experts on a variety of topics, and make sure that that it's understandable to the non-science community. So I'm also open to feedback from listeners if there's something that you would like for us to do that, and we'll see what we can do. Okay. Oh, no, that's not.
I was going to jump in there for a second, Ginny, just to
please.
say that there are parts of the report, there are summaries before each section. And again, at the end for some of them that are probably more accessible than the nitty gritty of the details within each section. And if you're someone who is somewhat daunted by technical language, I might suggest starting there. And the target of this report was scoped. So the target audience was scoped kind of broadly as the attendees of the Salish Sea Ecosystem Conference, which includes a very wide range of people. And so that was sort of a broad audience to try and hit as well. But it's definitely less technical than a scientific manuscript, although there are lots of references for readers who want to go further. But the section summaries might be a great place to start if you're just trying to get your sink your teeth into this somehow.
Great suggestion. Hey, Aquila, is there anyone else in the cartography world that you're aware of working on similar issues of Salish Sea mapping?
I don't know of anyone who's doing comprehensive mapping quite like this. And if they're here, they should tell me that they're doing it so we can work together. And you had a question earlier about how comparable the issues are to other areas. And I think that the spatial data issue is particularly challenging for us since we cross an international border. And I think collecting data and communicating effectively with maps or any format is challenging for managing, any of our coastal areas, but this international border does make this extra challenging for sure. So that's something that's perhaps not entirely unique, but a little different about our region.
True enough. And interestingly, I mean, we're two countries that speak the same language, that are on friendly terms, and you would think a lot of this would be easier, but it's not. There was a really interesting paper done by somebody who came in from Estonia with the Border Policy Research Institute, a colleague, and her finding of a report was that in Estonia, collaboration was easier with their surrounding countries than it is here, which was fairly interesting. Aquila, while I've got your attention, I wondered if you could also just speak to the whole Fraser River issue and the fact that the map doesn't show the entire drainage of the Fraser River, which I know is a difficult thing to include. Do you want to just speak to that upper watershed issue?
Sure. So I guess I'm going in the kind of the tradition of the other regional definitions that have been used in the past to say that if we kind of follow the mountains and jump along over the Fraser River, there is this kind of naturally obvious coastal region with more similar climate and ecosystems on the coastal side of those mountains. And so you would just follow the Fraser River up to the rest of that drainage basin. It starts to feel different and like a much larger area that's difficult to map comprehensively. But it's true that, I was trying to say, I'm following legal definitions, but when we're talking about the region that influences the sea, the region of the watersheds, there is no official definition of that. And we're each kind of making it up, which does make it difficult to make things comparable. This makes sense to me intuitively and from my knowledge of the ecosystems, but someone else could make a different decision about it that would be equally valuable and correct.
Yes, indeed. Okay, here's a question about modeling for Kathryn, I believe. Is there a comprehensive digital model or simulation for the Salish Sea ecosystem?
I'm not sure how to answer that. I'm not sure what aspects, biological, physical, chemical. There are some integrated, what we call end-to-end models that are being developed at NOAA Fisheries and in BC as well, at UBC. So there are several different modeling enterprises going on, and sort of the end game depends on what the objectives of the model. It's a tool like anything else. And so I'm not sure I'm not really sure how to answer without a little bit more information.
Oh, yeah. Okay. And we'll also refer people to the report where there is some vignette about modeling that may be of relevance. Before we're starting to get low on time here, and we are looking at planning future symposia on different topics. And if people would like to post in the chat box something that you would really like to see us focus on for future symposia, please feel free to do that. I'm intrigued at the conversation that was there for a while about, it seems like there's an opportunity to bring stormwater experts together specifically to share information. Certainly the Salish Sea Ecosystem Conference does that. Happy to help if there's more need for something in the interim between those conferences. Here's a question about freshwater input into the Salish Sea. What do we know? What % is glacier snowmelt versus rainfall, and how will this change with climate? That's beyond our...
I believe we probably have these calculations, and it will change with climate. And some of that is outlined in the report. I don't have the figures right off the top of my head, but there is more information there. And that's sort of an area of work that's actively being pursued by the Climate Impacts Group and probably Pacific Climate Consortium too.
Oh, yeah. Well, and while we're on the climate, I think this one is for Emily. Can you address the intersection of sea level rise and increased stormwater runoff on the health and habitat of the Salish Sea? And this will likely be our last question.
Sea level rise and stormwater. That's an interesting intersection that we haven't explored particularly. I do a lot of estuarine restoration, so we think about sea level rise in that perspective, and we think about that as it intersects with sort of the diminishing amount of fresh water coming out of river systems from a diminishing snowpack. But I haven't actually thought about that in the context of stormwater, other than in the very low-lying areas. Not so much in the Salish Sea, but throughout the nation, we actually have, the stormwater drainage systems in Florida, for example, on king tide events, so really high tides, the stormwater drains flow backwards. And so you actually have geysers coming up out of, the sidewalk many kilometers inland. And so that sort of stuff, from a flow drainage standpoint, we do see backups of stormwater in sort of the lower lying areas as a result of those tides, not to the extent that we're seeing in Florida. But the bigger issue that we see is that when we have intense rain events, we have an overflow situation. And so that's kind of the climate signal that is most troubling from a stormwater perspective. And so when we have overflow events, basically there's things called CSO basins that are combined sewer and stormwater runoff. And so when you have an overflow event, basically they have to just open up the gates and they let all the sewage and the stormwater dump directly into the waterways because they just can't handle that amount of flow. So that's kind of the main climate stormwater intersection that people are dealing with in our region.
Great, thank you, Emily. Well, I'm going to remind us of a few things. This was being recorded and will be available. The link to the recording will be available in a few days for everybody who registered for the symposium. I really want to thank all of our speakers so much for covering a lot of territory and sharing your knowledge with us. Thank all the audience, Western Washington University Alumni Association providing the technical support and platform for this, and folks who have donated to the Salish Sea Institute. We'll see you at our next symposium, June 10th, and look for additional ones that will be posted on our website. All right, take care. Bye, good night.